Dear students, very good morning and welcome to the lecture series session on EC402 Nanoelectronics of Kerala Technological University. Today, we are going to discuss about the hot electron transistors. In the last class, we have discussed the transport of electrons through heterojunctions, what are its properties, and what happens to electrons when it is subjected to an electric field. And we know what are photoelectrons. Today we are going to discuss a new device which works on the principle of hot electrons, the hot electron transistors. Let us see what are all its features and how it operates. Hot electron transistors. As we know, when electrons are accelerated under high electric field, they can acquire energy much higher than those corresponding to the thermal equilibrium. When the semiconductor is in the thermal equilibrium, the electron temperature Te coincides with the temperature T of the crystal structure. Under non-equilibrium conditions, when an external electric field is applied to the electrons, they are accelerated at very high velocities and possessing the velocity energy, that is the kinetic energy. The kinetic energy and thus the temperature Te of the electron can reach values which are usually much higher than those corresponding to the temperature of the crystal. The electrons under these conditions, that is under non-equilibrium conditions, are called hot electrons because these hot electrons will not obey the thermodynamic equilibrium principles. Heterojunctions between different gap semiconductors allow the generation of hot electrons. Since the electrons will acquire high kinetic energy given by the energy discontinuity in the conduction band delta Ec when traveling from a wide bandgap semiconductor to a small bandgap semiconductor. In the case of aluminum gallium arsenide heterojunction, the value of this delta Ec, that is the energy discontinuity in the conduction band, that is delta Ec. That delta Ec ranges from a value 0.2 volt to 0.3 electron volt, to 0.2 electron volt to 0.3 electron volt. And that you can see that is about 10 times higher than KT is equal to 0.026 electron volt at room temperature. That is under thermal equilibrium condition, this KT is equal to 0.026 electron volt, and that is far smaller than this value, delta E. And this corresponds to a carrier velocity higher than 10 raised to 8 centimeter per second. When the electron travels across the junction, the electron beam suffers a collimating effect as a consequence of the acceleration suffered by the electrons in a direction of the electric field perpendicular to the interface of the junction. And this effect is called the electron injection by heterojunction, that makes the outgoing electrons concentrate inside a cone of about 10 degrees of aperture. The most energetic electrons in a given distribution is selected by making them to cross the potential barrier. But the barrier has to be very thin. In order to cross the potential barrier, the barrier has to be very thin. Another procedure to do this is to inject the electrons from an emitter, and this is based on the formation of thin potential barriers in the conduction band of the semiconductor structure so as to allow these electrons tunneling through the junction and resulting the electron beam which is more or less monochromatic. In hot electron transistors, the carriers injected from the emitter have high potential or kinetic energy on the base. Since a hot carrier has a higher velocity, that is why it is called hot electron. Hot electrons have higher intrinsic speed, higher current and higher trans conductance, and that is why it is called tunneling hot electron transfer amplifier. In hot electron transistors, the carriers injected from the emitter to the base have high kinetic energy that we have seen. Now let us consider the typical structure of an aluminum gallium arsenide hot electron transistor that is shown here. The emitter and collector are heavily doped N-type gallium arsenide, which is usually a very thin intrinsic gallium arsenide emitter barrier is provided between emitter and base. This is the base, and base is also a lightly doped N-type gallium arsenide, and this is the emitter, which is a heavily doped N-type gallium arsenide. Between the emitter and base, an aluminum gallium arsenide spacer or layer is formed. Similarly, the collector is a heavily doped gallium arsenide. In between the base and collector, a collector barrier is also provided, and the thickness of this collector barrier is about 3000 angstrom unit. Similarly, base, I told you, base is a lightly doped N-type gallium arsenide material which is having a thickness of about 1000 angstrom, 1000 angstrom units. So it's very thin compared to the collector or emitter. The connections to the emitter, base and collector are made with metallic contacts as shown here. This is the base metallic contact, and this is the emitter metallic contact, and this is the collector mechanical contact. Now let us consider the operation of this device and how this device is operated, and the energy band diagram also we will see here. Usually the transistor will be operated by giving suitable biasing on its base. The base is positively biased with respect to the emitter. When a positive voltage is applied to the collector, the injection of hot electrons from the emitter takes place by tunneling through the thin aluminum gallium arsenide barrier here that we have seen. See, when the emitter emits the electron which crosses this emitter barrier, and reaches at the collector. So emitter is injecting the electron from emitter to the base. The effective thickness of the barrier can be modulated by varying the voltage difference between the emitter and base. Voltage between the emitter and base is the VBE. So by varying VBE, the effective thickness of the barrier can be modulated. The velocity of the injected electrons will be almost 5 into 10 raised to 8 centimeters per second, and the electrons are seen to be collimated inside a cone of about 6 degrees. Now the current gain of this device. The current gain through the base, that is alpha, and usually the value of alpha will be almost equal to unity, and that can be made unity if both the scattering in the base region and reflection in the collector barrier are reduced as much as possible. That is, this different when the electron crosses the junction. Of course, we have already seen scattering takes place, and if this scattering is reduced as much as possible, then we can make the current gain value alpha to be almost unit. The base transit time can be of the order of tens of femtoseconds. That is, the base transit time means when the emitter emits the electron, which crosses the barrier and reaches at the base, and due to the biasing at the collector, this electrons are transit to the collector. So this transit time of electrons through the base will be of the order of tens of femtoseconds. Femtosecond means 10 raised to 15 seconds. But the crossing of the collector barrier is usually it will take much more time than that of the base because the collector barrier is thicker. That we have seen about 3000 Armstrong units. No. The collector is having a thickness of 3000. That the collector is having a thickness of about 3000 Armstrong units that we have seen, and that collector barrier that we have already seen here, the collector barrier is about 3000 angstrom unit thickness. So the thickness of the collector barrier is higher as compared to the emitter barrier. So it will take more time to transit electrons through that barrier. The total time of transistor, the total time of transit means total time of transit of electrons from emitter to collector is about 1 picosecond. The transit time can be reduced by reduction in the dimension of the hot electron transistor. That is, by the reduction of the thickness of space charge region by increasing the doping level. But increasing the doping level causes what? Increasing the doping level causes the impurity diffusion that makes the device more complex. So, in order to overcome this phenomena, the base of the device is made of a metal such as cobalt inside that is a non-contaminant and does not show electromigration with good conductivity as that of metal. So, in order to avoid this kind of impurity diffusion effects and all, we actually make the device made up of metals such as cobalt silicide, COSI2, which has got a very good conductivity at the same time. Very good electromigration is also possible with that material, and moreover with the non-contaminant material. So that will give the electron movement very fast. And such devices are usually called metal-based transistors. With this discussion, we will complete the session on hot electron transistors. Thank you.